This is section 4.4, trigonometric functions of any angle. Trig functions on the non-unit circle. Now, this isn't an official title for the circle, I'm just calling it that to distinguish it from the unit circle, because in this particular circle on the screen, we don't have a radius of 1 necessarily. It's a radius of any value. So we're going to talk about the trig functions when we look at right triangles that are inscribed in circles of this nature, where r can be any value. Sine theta equals y over r, cosine theta equals x over r, tan theta equals y over x, cosecant theta equals r over y, secant theta equals r over x, cotangent theta equals x over y. I'm going to explain where each of those comes from, but before I do, I just want to put this whole lesson in context. The reason it's called trig functions of any angle is because up until now what we've been doing is we've been calculating trig functions for acute angles. And of course, as you know, when you're dealing with a right triangle, all the angles are acute, or 90 degrees, but there's no angle that is greater than 90 degrees. And so the nature of right triangle trigonometry deals with acute angles. So how is it possible, many students of trig wonder this in the beginning, how is it possible to get the sine, cosine, tangent, cosecant, secant, or cotangent for a non-acute angle? And that's what I want to explain first. Okay, let's look at this example. It doesn't matter what value theta has or what value theta prime has. What matters is the concept. Here we have a right triangle that is inscribed in the circle in the second quadrant. Recall from the very beginning of this chapter the quadrants. You know, we have quadrant 1 that I'm circling now with the mouse arrow, quadrant 2, quadrant 3, and quadrant 4. So this particular right triangle happens to be inscribed in quadrant 2. If we look at the terminal side of this angle, that's r, the initial side is still the positive x-axis. That hasn't changed. The initial side is still the positive x-axis. However, the angle theta, if measured from the positive x-axis, has a magnitude that's greater than pi over 2. That is greater than 90 degrees. Alright, so this is definitely an obtuse angle. It's non-acute. What we are really doing when we calculate the sine, cosine, tangent, cosecant, secant, or cotangent of an obtuse angle, what we are really doing in that case is we're actually calculating the reference angle, the trig functions for the reference angle. What we mean by a reference angle, in this case I'm marking it as theta prime. The reference angle is the acute angle that is in the same quadrant as the terminal side and touches the x-axis. Notice that this theta prime meets those criteria. Theta prime is in the same quadrant as the right triangle. It's in the second quadrant. Notice also that it's the angle closest to the terminal side that also touches the x-axis. Alright, so that's where reference angles come from. Reference angles always must touch the x-axis. Sometimes students get confused by reference angles, and I'm showing you this now because I don't want you to fall into this mistake. But sometimes if a student sees an angle like this theta here, they'll think that the reference angle is this angle here. Alright, but that of course is not true. That is not the reference angle because it doesn't touch the x-axis. The reference angle must be adjacent to the obtuse angle in question, and it also must touch the x-axis. Alright, so that's enough about reference angles, and keep in mind then of course that the trig functions really apply by definition to acute angles, but we can extend trig functions to obtuse angles by considering their reference angles. Okay, so let's explain now where these come from, the definitions, sine theta equals y over r. Well, it comes from the same definition of sine that you've already learned. If this point x and y here is on the circle, well then the length of the leg that goes from the center to where this dotted line begins, the length of that leg is the value of x. And the length of this leg, the vertical leg, defined by this dotted line here, is simply the value of y. And therefore, if I'm looking at my theta prime here and considering it opposite over adjacent, opposite over hypotenuse, well, the same is still true. Looking at this theta prime, the opposite side has a magnitude of y, so it's a distance of y units, and the hypotenuse, which is our r, has a distance of r units, and therefore the sine is opposite over hypotenuse, which is y over r. The same is true of cosine. The cosine is adjacent over hypotenuse. The adjacent in this case is the x distance, and hypotenuse is still r, and so x over r is cosine. And the same logic applies to all of these definitions. Tangent theta is opposite over adjacent, y over x. Cosecant theta is simply the reciprocal of the sine, therefore y over r becomes r over y. Secant, the reciprocal of cosine, therefore x over r becomes r over x. And cotangent, the reciprocal of tangent, and therefore y over x becomes x over y. Alright, so this is just where we get the definition for trig functions of any angle, whether it's acute or obtuse. Now you might ask, well, what's the difference? What's the difference if we're using reference angles? The difference is that quadrant matters with non-acute angles. Quadrant matters. And this is why quadrant matters. Let's look at this example. Find the 6 trig functions of the point -12, -5. So the first thing to do, let's plot that point. -12, -5 is plotted in the third quadrant. And we can calculate the r just based on the Pythagorean theorem, because if this is -12, -5, then the dotted line has a distance of 5 units, and the part of the x-axis that goes up to the beginning of the dotted line, of course, has a distance of 12 units. 5 squared is 25, plus 12 squared is 144. Add those two together, you get 169, and the square root of 169 is 13. Alright, so the r equals 13. You can find that easily on your own. That's usually an important part of these kinds of problems. But the reason that it matters what quadrant you're in is because that will determine the sign, that is the positive or negative sign. That'll determine the sign of the particular trig function that you're calculating. Okay, so using the definitions that we just learned that are in the upper right portion of this screen, find all the trig functions of the point -12, -5, and then resume when you have an answer. Alright, so you should have come up with sine theta equals -5 over 13, cosecant theta equals -13 over 5, cosine theta equals -12 over 13, secant theta equals -13 over 12, tan theta equals 5 over 12, cotangent theta equals 12 over 5. Okay, so here's where sine comes into play. Now let's look at this angle, the angle that's associated with the point -12, -5, and follow what I'm doing now with the red pen. First, I'm going to trace out my theta. Okay, I'm going to trace out my theta. And if I trace out my theta, it looks something like this. Starts at the positive x-axis, goes all the way around, and that is my theta. Alright, if that's my theta, then my theta prime is right here. Theta prime has to be in the same quadrant as the point, and it also has to touch the terminal side, this radius, and it touches the x-axis. So this little red line here is my theta prime. So I can indicate that here, theta prime. Okay, so I've got my theta prime. But notice that we're asked to find the sine, cosine, tangent, cosecant, secant, and cotangent of theta, not theta prime. If I just found it for theta prime, all the values, of course, would be positive, because I'm simply dealing with an acute angle. But since I'm dealing with this large obtuse angle, I need to consider what quadrant the angle is in. And that, of course, is determined by the sine of the x-coordinate and the sine of the y-coordinate. And since both x and y coordinates are negative for this point, I'm dealing with the third quadrant. And therefore, I have the corresponding signs for the trig functions. The sine of theta is negative, so is the cosecant. The cosine of theta is negative, and so is the secant. The tangent of theta is positive, and so is the cotangent. And why is it positive? Simply because the negatives cancel. Negative 5 over negative 12 is simply positive 5/12. All right, now some of this, what's on the screen, might seem like common sense to you. But the reason that's important to go over now is because we will be calculating a lot of trig functions for non-acute angles. So it's important to be familiar with the quadrants that angles can be in, and of course familiar with the concept of a reference angle. Signs of trig functions of any angle. Now, I put this table here for your benefit. You don't necessarily have to memorize it. I do want you to write it down, but then I'll give you an option that I'm about to explain. Okay, first of all, this simply tells you that for an angle in quadrant 1, the sine, cosine, and tangent are always positive. And I put in parentheses cosecant, secant, and cotangent because, of course, once you have the sine of an angle, you also know the sine of the reciprocal function. And as you know, cosecant is the reciprocal function for sine, secant the reciprocal function for cosine, and cotangent the reciprocal function for tangent. So those signs always match. It's also in parentheses because many tables simply only have sine, cosine, and tangent because they assume that you know that the sine of the reciprocal functions are identical. All right, so the table then going on, quadrant 1 angles have sine, cosine, tangent, all functions are positive. In quadrant 2, the sine and cosecant are positive, all the others are negative. And you can verify why that's true by going back to the definitions here on this previous screen. Definitions on the previous screen show all the trig functions in terms of y, r, and x. And so the signs of x and y determine these depending on quadrant. Okay, in quadrant 3 we have cosecant, sine, secant, and cosine negative, cotangent and tangent positive. And again, just flipping back to the last page, we verified that here because we had a quadrant 3 angle. And sure enough, the tangent and cotangent were positive, but everything else was negative, just as it is in the chart here. And finally, in quadrant 4 angles, sine is negative, cosine is positive, tangent is negative, and the reciprocal functions have corresponding signs. All right, so the option that I alluded to in the beginning was that I do want you to write this down, but you don't necessarily have to memorize it. Some students like to memorize it. They come up with mnemonic devices. For example, you could think of it this way, going counterclockwise from quadrant 1 to quadrant 4. If I go counterclockwise, I can say, plus, 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 minus, 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 plus, minus, plus, minus. You can do that. You can figure out any kind of mnemonic device you want to figure out. But you don't have to memorize, okay? Some students prefer not to. And I'm not sure which way is better. I think it just depends on your preference. Some prefer to memorize, some don't. But if you don't memorize, just know that for any point or any angle, you're going to have to sketch to determine what quadrant you're in. And then if you can think, in each quadrant, if you can think in terms of whether x is negative or positive or whether y is negative or positive, then you will get the right sign for the trig function. Okay, so I'll leave that up to you. Copy down the chart, Memorize it if you wish. If you don't wish, just keep track of which quadrant your particular angle is in. Classwork, page 318. Write these numbers down, please, and see you in class.